Hello, everyone, and thank you for attending my talk. Today I'll be discussing binding of perfluoroalkyl substances to different serum albumins, specifically looking at human and bovine serum albumins. You'll notice that this is a collaborative effort between myself and the Department of Chemical Engineering and also a fellow graduate student, Alicia Crisali, in the Department of Biological and Pharmaceutical Sciences. And the reason that this collaboration has been possible is due to the group at the University of Rhode Island, as well as the Harvard T.H. Chan School of Public Health and the Silent Spring Institute called STEEP, that sources, transport, exposure, and effects of PFASs. So it's been a great experience to be able to interact with many different people in different disciplines, because I think it's allowed me to learn more as a researcher myself. The reason that we're interested in PFASs is mainly due to their widespread exposure and adverse health effects. We know that once PFASs are created from chemical production and manufacturing facilities, they end up in industrial and consumer products. They also end up in things like soil and groundwater and in water treatment plants. This gets them into human drinking water and thus into the human body. And then their transport through the human body, we know that they can stay in the body for on the order of years. So that's really where we are focused, where my group is focused, that once these chemicals go into the human body, where do they go and why? And how can we start building models to predict that? We know that protein binding and cell membrane partitioning disrupt cellular processes. We also know that PFAS bioaccumulation models rely on both lipid and protein association, and this also depends on the type of PFAS. This is unique to PFASs because typically you don't need all of that information in order to create predictive bioaccumulation models. So things like protein binding constants have been used to predict placental transfer efficiency. That's the plot I'm showing you here in a study in 2019, where they related the dissociation constant from HSA, human serum, and fatty acid binding protein to the placental transfer efficiency of different PFASs. That's the efficiency of the PFAS to transfer from mother to child. This is why we're focused here on protein binding constants, because in order to do these types of analysis where you're comparing and predicting biological endpoints, you need the most accurate values of Ka or Kd, so association constants that you can obtain. We decided to focus on the most common experimental technique using PFASs and serum albumins. So here we're looking at fluorescence quenching. And as PFASs start interacting with this hydrophobic pocket, whether it's in BSA, which I'm showing on the top, or HSA, which I'm showing on the bottom, you see a decrease in the fluorescence intensity of the intrinsic fluorescence intensity of the protein itself. And based on that, you can do an analysis. The most common analysis is the Stern-Volmer analysis, where you take the change in fluorescence intensity and compare it to the concentration of ligand. Then you can obtain typically a straight line, where the slope of that line is equal to the Stern-Volmer association constant. That's what we're after here. There's a subtle nuance in the derivation of this analysis, however, that we've discovered. This concentration of Q, typically people just use the concentration of PFAS that they've added to the system. The reason why that's not quite valid is this concentration is supposed to be the concentration of free quencher, so the concentration in the bulk phase. All you know when you do this analysis is the concentration that you've added to the system. If this value is high, then you can use this as an approximation of the free PFAS. But the number has to be high and the binding has to be quite small. We know that PFASs bind to HSA and BSA with a high efficiency. So this type of analysis isn't necessarily reflective of the conditions in the mixture. And as you go to higher concentrations, so where this should be a little bit more valid, the the plot starts to saturate. So the protein and the fluorescence start to saturate. So people have used the modified Stern-Volmer analysis, where you now introduce this fractional accessibility value, where you're saying that a PFAS that's on the surface doesn't have the same chance to quench the fluorescence as one that's in this hydrophobic pocket. And that part of it is great, but the only problem here is that you still have to assume that once this complex is formed, it's no longer fluorescent. So the saturation effect sort of negates the ability to use this type of analysis. A model that's more reflective of the real conditions and we believe is more appropriate is this Hill model. It was first introduced into the PFAS world in a paper in 2010, where now we have this residual fluorescence term. That is what accounts for the saturation effect. And we can obtain a Hill association parameter and the number of binding sites. So here what I've done is compared the Stern-Volmer association constant to the Hill association constant for a few different PFAS, specifically carboxylic acids, as well as octanoic acid. You'll notice that compared to the Hill model, the Stern-Volmer and modified Stern-Volmer values are lower. And we believe that the Hill model more appropriately reflects the system for the reasons I mentioned. The saturation effect is accurately captured by the Hill model. We can also do this, so the data that I showed you previously is specifically for bovine serum albumin. We can also do this for human serum albumin. And here you can see that even at high concentrations, so the same thing, we see the saturation effect on the change in fluorescence intensity as we add PFASs to HSA. It actually happens sooner than it does with BSA. So we, again, believe that the Hill model is the most appropriate for this situation. We've also used a different type of fluorescence technique, a more novel technique, where the company Nanotemper has created an instrument called the Tycho NT6. And what happens is you add your PFAS and BSA mixture to the instrument, and it scans the fluorescence at 350 nanometers over a range of temperatures. So this allows us to very quickly and easily determine the fluorescence intensity at many different temperatures, and to look at the absorption behavior of PFASs onto either BSA or HSA. If you take a cross section, it's the same type of analysis that we've done. So at 35 degrees, you can see the change in fluorescence intensity, and you could obtain whatever type of constant, whether it's Hill or Stern-Volmer or whatever that you'd like. The nuance of this method is that we can see what's happening at these points. So here we're looking at the inflection points of the curves, which is indicative of the melting temperature of the protein. You can see that for PFOA and BSA, we see a slight difference in the change in melting temperature as we add different PFASs. We don't necessarily see that with PFNA or PFDA, but there's a difference in how this protein responds to the presence of PFAS. And similarly, you can do the same type of analysis with HSA, where you see an initial drop in fluorescence intensity, but then sort of a steadying effect, which is similar to what we saw with the fluorescence quenching results, where you see an initial change in fluorescence, but then it sort of saturates. This is true not only for PFASs, but also for fatty acid analogs. So looking at the unfluorinated version of the molecules, you see different behavior for octanoic acid versus PFOA. But for non-anoic acid, you see that there is a conformational change occurring, and you see a relatively large drop in fluorescence intensity. And we believe that this is due to the structure of non-anoic acid being sort of a good fit for that hydrophobic pocket within bovine serum albumin. This could be the case as well for human serum albumin, because we see this initial change in fluorescence intensity and then everything staying steady. So in summary, I've shown that binding to BSA and HSA can aid in PFAS transport predictions within the body, but that proper analysis of the fluorescence quenching results is vital to obtaining binding constants. We additionally saw with the Tycho analysis that conformational changes occur upon binding of some PFASs to BSA. With that, I'd like to thank all of my collaborators at STEEP for making this project possible, as well as the NIEHS Superfund Research Program, as well as the undergraduate researchers that I've been working with. And thank you, and I'm happy to take any questions.